Hello, everyone. We called our paper a near-optimal two-pass streaming algorithm for sampling random walks over directed graphs because we found this title very catchy. But for this talk, I'm going to work with a more scientific title, which is simply random walks in small space. So let's start. Random walks can be studied on both directed and undirected graphs, but we shall only focus on directed graphs. A directed graph is simply a set of vertices. We shall use n to denote the number of vertices, and a set of edges that connect pairs of vertices. An example is in the picture. And a random walk over a directed graph is defined by a start vertex S and a parameter L, which is the length of the random walk. To get this random walk, you start from the start vertex and you sample one of its out edges uniformly at random. So there are only two. Let's say you pick this one, and you follow this edge to get to the next vertex. So this is one step of the random walk. And now that you're at this vertex, you sample one of its out edges. It has three, and you again pick one uniformly at random. Let's say this one, to reach the next vertex. This is the second step of the random walk. And you do this for L steps to get an L step random walk, which will just be a path in the graph. Why do we care about random walks? The reason we care about random walks so much is because they have a lot of applications in problems we are interested in. Perhaps the most famous application of random walk is in the PageRank procedure. That is essentially just a random walk over the internet graph. There are other applications, such as some clustering algorithms utilize random walks as they help determining the connectivity structure of a graph. And random walks also find use in some machine learning models. So there are plenty of interesting things that we want to do with random walks. And we are lucky to have a very simple algorithm for computing them. In fact, the algorithm is just what I described. You start from the start vertex, and for each step, you sample an out edge uniformly at random. This algorithm takes essentially a runtime of L, which is the length of the random walk, and can easily be shown to be necessary because the output is length L. So the runtime of this simple algorithm is very nice, which is great. But what is not great is that this algorithm assumes that you have random access to the graph. Indeed, we need random access because when we are at a given vertex in the graph, we need to know all its neighbors so that we can sample one of them uniformly at random. And this is easy to do for small graphs that can fit in your memory, but for very large graphs, say the internet graph or a graph of social network, you do not have enough memory to keep the entire graph, and this process becomes expensive. The way around this problem with large graphs is to use a streaming algorithm. So let's see what they are. A streaming algorithm for a graph is as follows. The input is a graph, of course. The vertices of the graph are known to everyone, but the set of edges is presented to the algorithm in the form of a sequence. The algorithm can make one or more passes over the sequence, and in each pass, it gets to visit each edge in the sequence one by one. When it visits an edge, it can do an arbitrary computation using its current memory state and the value of the edge to get to its next memory state. But when it leaves the edge, it must forget everything about it and work only with its memory state. Because we allow the algorithm to do an arbitrary computation, if the algorithm has enough memory to remember the entire sequence, it can compute any function. And the interesting problem is to given a certain function f, in our case, this will be the random walk function, find this algorithm with the smallest amount of memory in the fewest number of passes that can compute this function. This is not a new question. Streaming algorithms for random walks have been studied since a long time, but all known algorithms either use a lot of memory or a lot of passes. For example, there is a very easy L-pass streaming algorithm for random walks, which just tries to simulate each step of the random walk in each pass. So in each pass, it only needs to sample the neighbors of one of the vertices, and this can be done with very low memory, with only log-in memory. And this gives us a log-in memory L-pass algorithm. In 2011, SGP came up with a very clever algorithm that used n memory, but they were able to shrink the number of passes from L to root L, so a quadratic improvement. But it turns out that even root L passes are too much for most applications, because in each pass of the streaming algorithm, the algorithm has to traverse all the edges in the graph, and therefore each pass is very expensive, and we want the number of passes to be as low as possible. In the extreme case, we want the number of passes to even be 1. And we actually have an algorithm that takes exactly one pass. It's an easy algorithm that I'll talk about later. But for now, it takes exactly one pass, but it needs NL memory to compute the random walk. We also have a matching lower bound showing that if you insist on having only one pass in your algorithm, then NL memory is needed. And this raises the question, this lower bound really depends on the algorithm only having one pass. Can we significantly save on memory if we have more passes? It turns out that streaming algorithms in general are very delicate to the number of passes. If you change the number of passes even slightly, that can greatly change the amount of memory needed. For example, there are known problems that are very hard for one-pass algorithms, but if you increase the passes to even to 2, then they start becoming easy. And there are also problems that are very hard for one-pass algorithms that stay hard throughout, let's say till log n or root log n passes. So it really depends on the problem how the memory behaves with the number of passes. And we want to study this for the random walk problem. Specifically, we want to know what happens to the memory if you start increasing the number of passes slowly. So what happens if the number of passes is 2? What happens if it's 3? What happens if it's 10? And so on. We have partial results for all number of passes, but our main result is showing that for 2-pass algorithms, n root L space is both necessary and sufficient to compute a random walk. Let's see this in more detail. So first, we show an algorithm that takes 2 passes and n root L space to find a random walk. We show that this algorithm is tight. And not only is this algorithm tight, it actually has this nice property that it works in the stronger turnstile model. This turnstile model is a generalization of the streaming model. If you recall, in the streaming model, the edges are presented as a sequence, and the algorithm can make passes over the sequence. This is equivalent to saying that the algorithm starts with a blank graph, and as it gets the edges, it adds these edges to the graph. The turnstile model is a generalization where not only can the input add edges to the graph, it can also remove edges from the graph. And our algorithm has this really cool property that even in the turnstile model, it outputs a random walk with the same space guarantee. Moreover, our algorithm has another nice property that it is actually oblivious to the start vertex, or it is an SVO algorithm. What this means is the algorithm actually does not care about which vertex the random walk starts from till the very end. For all its execution, for both of the passes that it's doing over the sequence, it can have absolutely no information about the start vertex. And only when it needs to output the random walk will it need the vertex that it's starting from. This means that the same algorithm with the same number of passes and the same space complexity can actually output an L-length random walk from all the vertices in the graph, because it doesn't need to know which vertex to start from. And that's a really great property. It outputs n random walks for the price of 1. For SVO algorithms, we can actually show a very strong lower bound. We can show that even if you increase the number of passes to any number you want, even if it's infinitely large, any SVO algorithm that finds an L-length random walk must have at least n root L space. So we are tight in a very strong sense. We have a 2-pass algorithm that does this, but even if the number of passes was 1 million or, I don't know, n squared, the algorithms that have the SVO property that output a random walk must have n root L space. We also have a lower bound for general algorithms. And for general or non-SVO algorithms, we show that if they have p passes, then they must have memory at least n times L to the 1 over p. In particular, if p is 2, then our lower bound for general algorithms matches our actual algorithm. And again, we have tightness. We need n root L space by the lower bound and sufficient from the upper bound. So we have 3 results. The first one is an algorithm that takes n root L space to find a random walk. The second one is a lower bound that does not depend on the number of passes, but utilizes the fact that the algorithm is SVO. And the third one is another lower bound that depends on the number of passes, but works for all algorithms. Both of these are tight for the case of 2-pass algorithms. And the hardest of the 3 results is actually this lower bound, the general algorithm's lower bound. And this is the one that I shall talk the least about. I will go and cover a lot of the details in the algorithm and in the oblivious lower bound. So let's see, and let's start with the algorithm. Now I want to describe a 2-pass n root L space algorithm for finding random walks. But for this, I first need to recall the 1-pass n L space algorithm for random walks. The idea in this algorithm is very simple. You have 1 pass over the sequence, and you use that pass to compute or to sample L edges with replacement uniformly at random from the sequence, from each vertex. So if L is 2, then from this vertex you have these 2 edges, this vertex you have these 2 edges. I'm not showing all the vertices because that will make the picture very cluttered. But for any vertex in the graph, you sample 2 edges uniformly at random with replacement, or L edges. And I claim that once you remember these edges, you can stitch together a path of length L from any starting vertex. So it will be an SVO algorithm. And given any starting vertex, the remembered edges suffice to stitch together an L length path. How will this be done? You start from the start vertex. Suppose you start here, and you have L edges from this vertex. So you take the first one. They're all uniformly random samples, so it doesn't matter. You take the first one, and you use that one to get to the next vertex. This is the first step in the walk. But you reached here where, again, you have L edges coming out of this vertex. So you again pick the first one and say you reach here. And this will go on for L steps. And it is crucial to note here that this path can actually visit the same vertex again, because we just picked edges at random and there's nothing stopping it from circling back to the same vertex. And when this happens, we can no longer use the edge we used before. We have to use a different edge, because in a random walk, every step is independent of every other step. But this is actually not a problem, because our algorithm has at most L steps, so it can only visit a vertex L times, and we already sample L edges from each vertex, so it will never be the case that we run out of edges. So this is how you compute an L-step random walk in an SVO manner. We did not depend on where S is in one pass and NL space. But our first observation is that this algorithm has an even stronger property. What this algorithm can tell us is that it can tell us exactly which vertices in the graph have a return time of less than L and which have a return time of at least L. In the context of random walks, a return time from a vertex U is the expected time taken by a random walk that starts from U to return to U. So it can be infinity if it never returns to U, and it can also be finite if it returns to U very often. And the claim is that our algorithm can actually tell in the same pass and space guarantees which vertices have a return time of less than L. The reason this is because our algorithm is SVO, it can actually be used to sample a starting vertex from each of the vertices, for a sample random walk from each of the vertices in the graph, an L-length random walk. And once we have an L-length random walk, we can just check if in L steps it returned to the same vertex or not. Of course, there are these issues about getting there with high probability and getting there with expectation, but those can be taken care of if you repeat it, let's say, log n times. So if you repeat it log n times, that doesn't really change the asymptotic behavior other than some lower order terms. You can compute in one pass and an L space which vertices have return time less than L and which do not. We shall actually use this procedure in the first pass of our algorithm. But we shall not use it with the parameter L. We shall use it with a different parameter K. Think of K as root L. We will set it to something around that later on. But for now, just think of it as root L. And we shall run this algorithm. And in the first pass, we shall know all the vertices that have return time less than K. We'll call these vertices the heavy vertices. And all the vertices that have a return time of at least K will be the light vertices. We can figure these out in order nk space. And this will be the first pass. In the second pass, our algorithm will store all the edges that come out from heavy vertices. And for the light vertices, it will take L over K independent samples just like before from each light vertex. Okay, so this is the description of the algorithm. It is easy to see that it has only 2 passes. It is also easy to see that it is SVO because I never referred to the starting vertex anywhere. I only need to show you that it actually does compute a random walk. The edges that you stored in the second pass can be stitched together to get a random walk. And I need to show you that it takes n root L space. Okay, so let's see why it does compute a random walk. And to compute a random walk from the stored edges, we will use the same procedure as before. We will start with a vertex, and we will see one of the edges we stored, and then we'll go to the next one, take one of the edges we stored, and so on. So if you have a heavy vertex, then you stored all its edges. And therefore, you will never be stuck at a heavy vertex. You'll never run out of edges. And if you are at a light vertex, then by definition of being light, it has a return time of at least K. So in your L-step random walk, you will only expect to be at the light vertex L over K times. And because we stored L over K edges from each light vertex, we'll never run out of edges of light vertices either. So we'll not run out of edges from heavy vertices, we'll not run out of edges from light vertices, therefore we'll not run out of edges, and we'll output a random walk. That's one part. Now I need to show you that this algorithm indeed takes n root L space. I already know that the first pass takes nk space, and I will show that the number of edges that are stored from heavy vertices is another nk, so that is just nk, and the number of edges that are stored from light vertices is nl over k. Now nk plus nl over k is minimized when k is root L, and therefore the minimum value will be n root L, and that's our space model. So let's see for the light vertices. The light vertices, I want to show that there are L over K edges, NL over K edges in total. And this is actually trivial because we only store L over K edges for each light vertex. And because there are at most N vertices in the graph, the total number of edges we store is NL over K. The interesting claim is that the total number of edges coming out of heavy vertices is order N over K. N, not N over K, N times K. And this is what I shall prove next. In fact, I shall prove it in a sort of a contorted way. Instead of counting the edges that come out of heavy vertices, I shall look at where these edges land and analyze them from there. So the claim that I'll actually show is for all vertices V in the graph, there are at most order K many heavy vertices U that have an edge to V. And because any edge from a heavy vertex must land on some V, and there are only n possible V's, and each one has k possible things, the total number of edges from heavy vertices is order nk. So if I show this, the lemma follows, and I want to show this. So I fix a vertex V, and I use the definition of heavy to conclude that a random walk that starts from a heavy U will return to itself in less than k steps. Now, this definition has an expectation inside. It says that in expectation, it will return in less than k steps. But let us assume for now that this is true for all random walks. This only changes the constants in the big O, so it's not really a big assumption. And we shall assume that any random walk that starts from U will return to U in less than k steps. But if U is heavy and has an edge to V, then there are random walks that start from U and go to V. And these will also return to U in less than k steps. And this is only possible if a walk that starts from V visits U in less than k steps. So for any heavy vertex that has an edge to V, a watt that starts from V visits it in less than k steps. But a watt that starts from V can only visit k vertices in k steps, and therefore there can be at most k vertices that are heavy and have an edge to V. Overall, because we will do all of these arguments and expectation, there will be Markov inequalities everywhere, and we will get that there are only order k heavy vertices that have an edge to V. In total, there are only order nk edges coming out of heavy vertices, and the lemma is shown, and the proof of the algorithm is complete. Okay, so we did the algorithm, and in the remainder of the talk, I shall focus on the tightness results for these algorithms. This algorithm. Recall that we have two results. The first one is a pass-dependent result that shows that for p passes and general streaming algorithms, you need n times L to the 1 over p space to compute a random walk of length L. This is the harder result that I shall not go into. What I shall go into is the optimal result. This is actually a very clean and simple proof for algorithms that are SVO and any number of passes. And I'll show that these require n root L space. Why is that? Consider the following graph. I have my n vertices split into n over root L components of root L vertices each. These are C1 to Cn over root L. And each of these components is a random graph. So I put edges uniformly at random between these vertices. Now, because these edges are a random graph, this graph is a very good expander. And therefore, I know that a random walk that starts from anywhere inside this component will actually visit all the L edges. There are only L edges as there are only root L vertices. All the L edges in L steps with very high probability. And in other words, what I'm saying is if you start a random walk from within a component Ci, then an L length walk will output all of Ci. But our algorithm is oblivious to the start vertex, so it does not know where the walk is starting. And in particular, if it wants to output an entire component without knowing which one it is, it must be ready to output all the components. But if it outputs all the components, it outputs the entire graph. And the graph has n times root L edges. N over root L components, L edges per component, so n times root L edges. And it must remember the entire graph if it's SVO. And therefore, SVO algorithms with any number of passes must have at least a memory of at least n root L. Okay, that's it. This is the entire proof. And now let me quickly summarize the result and leave you with some open problems. I showed that there's a two-pass algorithm, that is SVO, that computes an L-length random walk on an n-vertex graph using n root L space. I showed that this is tight for SVO algorithms with any number of passes. I did not show, but we prove in the paper that if you have a p-pass general algorithm that may or may not be SVO, then that requires a space of at least n times L to the 1 over p. So for p equals to 2, we get the same n root L bound. And therefore, our algorithm is actually tight for 2-pass algorithms. But it may not be tight for 3-pass algorithms that are not SVO. And this is actually the first and the most obvious open question left from our paper. What happens if you have a non-SVO algorithm with 3 passes? The best upper bound we have is still n root L. The best lower bound is now n cube root L, and it is interesting to know which one of these two is the right answer. In fact, more generally, we want to know how does the space grow as the number of passes increases? What is the trade-off between the number of passes p and the space of the algorithm? And the space-pass trade-offs for random walks are interesting. We also want to know what happens if you have an undirected graph. A random walk from an undirected graph over versus that on a directed graph is similar, but they're also very different, because when you have an undirected graph, then you can use the same edge to go back and forth, but for directed graphs, this may not be possible. So it'll be interesting to see what techniques generalize and what new ideas are needed. And finally, I would propose a related but slightly easier problem, which is instead of outputting the entire random walk, just output the last vertex. This is easier because if you can output the entire vertex, you can obviously output the last vertex. But it is interesting. It will be interesting to see if the algorithms for outputting only the last vertex are significantly cheaper than algorithms that output the entire random walk. So let me stop here. Thank you.